Hey yo, what's up my future AI experts? Let me show you in this tutorial how to train your neural network to classify the images. But just let me do a quick recap of what we have done in the previous tutorials. In the previous tutorials, I showed you how to calculate the mean and standard deviation of your own custom dataset in order to apply the normalization techniques later to normalize your dataset. Also, I showed you how to apply some other transforms to make your model to be more robust. I showed you also how to show your images after the transforms have been applied, so you can see what you have done with them. And also I showed you how to create your train and test folders and specify the batch size in order to apply the mini batch gradient descent algorithm later. Okay, let's continue now, and let me show you how to also train the neural network. Let me just quickly define three functions which we're going to use in this tutorial and which we will implement later. Okay, guys, so as I said, three main functions. So first of all, we will need to set our device. So for example, if you have the decent GPU on your machine, we need to, obviously, it would be very beneficial to use it because it will speed up the training process and you'll train your neural network much more faster. Also, of course, we need the method to train our neural network, and obviously we would like to evaluate the neural network as well. Okay, let me start with the set device. Basically, there's one thing which is called CUDA, which stands for Compute Unified Device Architecture. It's basically a software which has been made by NVIDIA, which will allow you to use the parallel computing and will allow you to use your GPUs in order to train your neural network. So it will speed up your training neural network process. And in order to do it, let me just quickly implement this function. Okay, guys, so very short function. However, one thing to notice, sometimes when you, for example, install PyTorch or like Jupyter Notebook, basically it will not mean that CUDA has been already installed as well. Sometimes you will need to install the CUDA from the source. So if you have a GPU and you can use it for neural network training, make sure you actually have CUDA installed on your machine. But if you will use the cloud-based service, which is quite nice to use, in this case, if it provides you with the AI environment, in this case, the CUDA will be installed there already. So in this case, there will be no need to worry about that. Okay, guys, let's move on. Let's work on the train neural network function, basically the main function in this tutorial. As you can see, this function expects a lot of input parameters. Let me first of all declare all these input parameters and let me explain what all of them mean. And after that, we'll implement the function itself. Okay, so we start with the model. Basically, it's like the main thing. So the architecture of our model. And there are two options. The first option will be, of course, to make our model from scratch. So implement the whole architecture ourselves, specify all the layers and what will they do, apply some techniques. However, I don't want to overcomplicate, and probably it will not be that efficient because you can just use already existing models, which will do the work much more better and which will give you the better accuracy. So yeah, the second option is just to use already defined model, which has been created by some very smart researchers, and which is very efficient. And the model which I'm going to show you in this tutorial is called the ResNet 18 model. The ResNet 18 model, it was the winner of the ImageNet competition several years ago. Of course, right now there's some better models which got a better score on the ImageNet competition a few years after that. But ResNet 18 is still a super nice model and it's a very good start. And the good thing about PyTorch actually is that if you install PyTorch, it will also allow you to use this model without implementing and writing all the code. PyTorch will even allow you to use this model as the pre-trained model, because it comes with PyTorch usually. And basically, you just write one line of code and you load the Resident 18 model, and if it's pre-trained, it will mean that it already has been trained on the ImageNet dataset, and so it can classify 1000 classes, which might be quite useful. Actually, it might be super useful, because ImageNet was a huge dataset, and pre-trained model already knows how the world looks like. So let me first of all import some things. Okay, so these are the imports which we're going to use on this tutorial. And let me declare the model. So as I said, ResNet 18, very good start. And basically, yep, one line of code and we have loaded the model. Okay guys, so this bit is very important. So if you say that pre-trained is equal to true, it means it will give you the model which already has been trained on ImageNet. If you say pre-trained is false, it just will give you the model with the random weights, so you will start from the scratch. Okay, the next step will be to declare just a temporary variable. Let's call it number of features. Yeah, number of features basically is the size of each input sample. After that, we need to specify the number of classes. And as you know, for this tutorial, I'm using the dataset which is called 10 monkey species. So it has 10 different categories, 10 different species of monkeys, and that's why the number of classes basically is equal to 10. If you're using a different dataset, you need to check how many classes you have. So how many categories are you going to classify in the end? You need to specify that. Okay, we need to define another thing here. Okay, let me do it. Okay, so this bit is very important. Yeah, here we'll use our two variables which we defined here. Basically, what this thing will do, and n.linear. Basically, linear is a function that takes the number of input and output features as parameters and prepares the necessary matrices for forward propagation. This bit is very important. Now, we will use the function which we have defined previously, setDevice, in order to set our device. So, to check if we have CUDA available or not, and in case if we have CUDA available, we are going to use the CUDA. And of course, for our ResNet 18 model, we need to basically set this device. Okay guys, very important bit, the loss function. This is the function which shows the error during our training process. It basically allows us to train the neural network. So it shows how far or how close we are in terms of the correctness of our classification. It basically, yeah, just shows the error. And for this, in this case, for this tutorial, I'm going to use the loss function, which is called cross entropy. Cross entropy is a widely used loss function for the classification problems because it gives a greater penalty when incorrect predictions are predicted with the high confidence. It's very popular loss function. However, you might experiment and try to use another ones. Just check out the documentation online and you will see which other options you will have. And the last bit, the optimizer. Okay guys, so the optimizer, we're going to use the SGD optimizer, which stands for the stochastic gradient descent. And now you probably might ask me, like, mate, what is going on? We just defined the mini batch size here. So we are going to use the mini batch gradient descent algorithm, but you're telling to us that we're going to use the stochastic gradient descent algorithm. What's going on with you, mate? That's what you might ask me. However, guys, I will tell you one thing. I don't know why exactly, but basically, yeah, this optimizer is called stochastic gradient descent one, but if you specify the mini batch size, it will apply the mini batch gradient descent algorithm for you. So always good. And when you're using the PyTorch, the SGD optimizer is a very good option to use because it's very efficient and usually it will give you a very good result. And here's some parameters which you need to specify. Let me explain you. Of course, you basically need to pass the parameters of your model. I think this is quite clear. Then you need to specify the learning rate. So how fast are you going to learn? And be careful, guys, because a learning rate might be like the most important parameter in your neural network because it might affect the performance of your model very a lot. The learning rate is a hyperparameter that controls how much to change the model in response to the estimated error each time the model weights are updated. And in order to choose the right learning rate, you probably would need to experiment a bit because there's like, no golden rules which learning rate to choose every time. But the usual practice is to choose, I don't know, from 0.01 to 0.001 and then just, see how it performs. However, it's not always the case. Sometimes you might need to choose a different value. So you need to experiment with that. Okay, let's move on to momentum, which we say that it's equal to 0.9. What is momentum? So momentum is a method which helps to accelerate the gradients vectors in the right directions, thus leading to the faster converging. And momentum is one of the most popular optimization algorithms, and many state-of-art models are using momentum as well and are training the neural network with momentum. Usually, people would set up the momentum to be equal to 0.9 or to the similar value. So that's why we want to specify the momentum as well. And the last thing, which is called the weight decay. So what is it, guys? And I will tell you what is it. Basically, the weight decay will give us like an extra error to our loss function. It might help to prevent the overfitting. And because the dataset in my case is quite small, I don't know how many on average. It probably has like about 100 images per each training dataset category on average, and which in reality is not a lot. I will assume that if the pre-trained would be equal to false, and when I will train my neural network, I would assume that the neural network might overfit a bit. So that's why I will try to use the weight decay to prevent the overfitting. Okay, guys. So we have specified, I think, all the input parameters which we need. Let me just double check that the code works. Let me just call this function. Okay, so model is equal to ResNet 18 model. Okay, train folder, test folder, they're staying the same. So they have the same name. Criterion. So that's our loss function. And here's our optimizer and number of epochs. I don't know, guys. Okay, if pre-trained is false, I don't know, maybe let's say 100, I don't know, 150. So let's train it on a lot of epochs to see how it goes. Okay, it probably will kill my machine, but let's try. Okay, let me run everything. Oops, here's a typo. Okay, guys. So, yep, now it works. So all is good. We can move on the training neural network function and implement it basically. Okay, guys. So training, yeah. Let's start. First of all, again, let's set the device. I just have a variable. Now let's iterate through all of the epochs. So a simple for loop. And let's just print what's the current epoch number to keep track of all the information, which will be quite necessary. Okay, we need to make sure that when we are training the neural network, we need to make sure that the model is switched. The model is in the training mode because we want to train, so we want to update the weights. We need to make sure we switch the model in to be in the training mode. That's very important. Don't miss this line of code. Okay, let's define some variable to keep track of the current loss, like the running loss, the running score, like how many images we classified correctly, and yeah, and the total amount of images as well, all these things. Okay, guys, so now we can iterate basically through all of the batches inside our train loader, which we pass here and which we have defined here. So let's just iterate through all of the mini batches. So from this data, let's get basically the images and the labels of this data. Labels basically will specify the class to which all of the images belong. And it's inside the data variable. Also, we would like to convert images and labels to the CUDA if it's available to speed up the process. And also one important bit, let's calculate how many images are there in the batch. Obviously, we know that the batch size is equal to 32, so there's 32 images. However, when we get to the last batch, it might have a different amount of images. So let's keep track of total amount of images. Okay, and now let's move to the hard stuff, guys. Okay, guys, before starting the backpropagation, we need to set the gradients to 0 so that our parameters update correctly. We can do it simply by doing this thing here. Now let's actually get all the outputs from the mini batch, which our model produces. So, on the first iteration, it just will produce the random stuff. After that, like, when it will train on the mini batches, like, it will improve, and will start learning. But we need to get the outputs anyway. And to get the outputs, we just simply do model, and then pass the images, and it will classify. And will return the outputs in this variable. Based on these outputs, let's just get all the predictions which are inside the outputs variable. So let's check how the model has predicted everything. This one here is just basically, it specifies the one dimension to reduce. Make sure you do it. Now let's calculate the loss between the target and predicted K points. Remember, we are using the cross entropy loss function in order to do that, which we have defined here, and which we passed as this parameter. So we need to give to this function the outputs and also the labels. So outputs, that's like what our model has said, that's what the model classified, and labels is like the true value. So the exact label which all the images have. Okay, now important training process. We need to backpropagate to calculate the weight gradients. And of course, we need to update our weights. Now we can just update the running loss. Also, we can update the running amount of the correctly predicted images. So this is just basically, this is all training which we need to perform in order to train the model. Now let's just do some additional things. Let's just basically print the result values. We can say that the epoch loss is equal to the running loss divided by amount of batches inside the train loader. And we can also calculate the epoch accuracy. There's a lot of metrics how to calculate the accuracy of your epoch. I'm just doing to, for simplicity, I just will divide the amount of classified correctly by the total amount of images to just, say how many was the percentage of images that we classified correctly. However, guys, in my next tutorials, I also will try to explain you what other metrics you can apply in order to evaluate your neural network model. And now let me just print, something about the current results. Also, so once we trained on, for example, on the first epoch, we probably would like to evaluate the model, how it performs on this epoch as well. And in order to evaluate, we're going to call our evaluate model on test set method somewhere here. And of course, we will need to also implement this method a bit later. But right now, let me just call it. And it expects two parameters. So basically the model and the test folder, which we also pass here. So we're going to implement this method in a few seconds, but also just to finish the rest, let me just in the end print finished, and also let me just return the model itself. Okie dokie, my future AI experts. Let's just quickly implement the evaluation model on test set function, and then we can try to actually train the neural network and see which results we are going to get. There are two inputs which this function has, so model and test folder. Okay, when we are starting to evaluate the model, make sure, guys, that you switch the model from the training mode to evaluation mode. So this function will notify all your layers that you're in the evaluation mode. In this way, the dropout layers will work in the evaluation mode instead of the training mode. So if you want to evaluate, make sure you switch the modes. Okay, let's just declare some variables to calculate the total amount of images, how many of them we classified correctly, and yeah, basically, let's just declare these two variables quickly. Let's also set the device using our function, which we implemented in the beginning. Okay, now we would like to deactivate the autogradient engine by doing just, so this line of code basically will reduce the memory usage and speed up the computations. However, you will not be able to backpropagate, but we are going to evaluate the neural network on a test set, so we don't want to backpropagate, of course. That's why we are going to use the no-grad function. And now let's just iterate through all of the mini batches inside the test folder, batch by batch. Again, now similar thing as here, we can basically just copy these 4 lines of code to get our images and labels, and to calculate the total, to update the total amount of images, because as you know, we specified the batch size, of course, but when we get to the last batch, there's no guarantees that it will have 32 images inside the last batch. So just let's keep track how many images we have in total in our test folder. And now again, similar thing as here. We want to get our outputs of the model, and also we want to get the predicted images. So we can just copy and paste it here. We don't want to update the laws, to backpropagate, and all the other stuff which we are doing here inside our training function. So we just want to calculate, how the model performs, so we can just evaluate it. And that's why let's just update our predicted correctly on epoch variable. and increment the amount of images classified correctly. This is all the things which we're doing inside the for loop with the torch.noGradient. And when we go outside this with and for loop, we just basically calculate the epoch accuracy, again, using the similar technique as we used inside the training neural network function. We just basically calculate the accuracy and just print something, like print the score which we are getting. And basically right now we can start and we can try to train our neural network. Let me just quickly run everything to make sure that I didn't do any typos here and everything is correct. Okay, so here's the first error. Training folder is not defined. Yep, so because we call it train folder, not training folder. Let me fix it. Oh, actually here it doesn't calculate it correctly. Oh. So it seems that the code is working, at least for the training function. Let me wait a bit to double check that the evaluation function doesn't break as well. Wait, something went wrong. Oh, sorry guys, yeah, I spotted the mistake. This thing should stay here, yeah, for every single epoch. And then in the end we just return. Okay guys, now as you can see, it seems to be working fine. All the bugs have been fixed. Now I just will leave it running for 150 epochs and will be with you shortly to share the results. Okay, my future AI experts. So my 150 epochs of training have been executed and I'm going to share the results with you. So the pre-trained was equal to false. So we have started with the random weights. And let me just scroll a bit down to actually find what was the best accuracy which we got on the testing dataset. Okay, 86.4, that's good. 86.76, also good. Okay, let me scroll. Maybe we got 89.338, almost 90%. Did we get better somewhere? Okay, 89.7. Okay, almost 91. 91.2. Okay, guys, yeah, probably 91.544 was the best result. So we got like 249 testing images out of 272 correctly. So this is what we can achieve with the ResNet 18 model when the pre-trained is equal to false, which is quite good. However, you still need to try to tune your model because, changing one parameter might affect the accuracy of your neural network a lot. So you would like to experiment a bit and, change the things like learning rate, weight decay, your transforms, or some other things to make your model to generalize better. So I'm sure that if we will experiment a bit, probably we will find out some parameters which will give us even better results. So make sure you do experiments, guys, because they're important. However, guys, I'm going to show you something else. I'm going to improve the accuracy a bit. So as I said, we just trained when the pre-trained was equal to false. let me just train the same neural network with the same parameters when the pre-trained is equal to true. And I'm going to share the results with you very shortly. Probably we will not need 150 epochs. Actually, let me just copy it. Probably we will not need 150 epochs, so let me just do, I don't know, let's say 20 to see the results. Okay, and I'm going to copy this line of code. Okay, pre-trained is equal to true, the rest stays the same. Okay, let me run it and I will share the results with you in a second. Okay, guys, so I just trained my 20 epochs with the pre-trained equal to true. So with the model which has been trained on ImageNet. And as you might see, the results are very different. Just like, on the first epoch, the accuracy on the testing dataset is equal to 93%, compared to, for example, to the neural network, to the same model with the pre-trained equal to false. Here you can see the testing accuracy on the first epoch was equal to 21.6%. And as you might see here, we achieve much better results. So I'm not sure if it's the best one, but yeah, 98.897. Probably if I would train a bit more, maybe it would be more than, maybe it would be over 99%. Who knows? But as you can see, the results are like awesome. We get almost all of the images correctly. Yeah, on the training dataset it's 100%, but it is fine. But just like look at the testing dataset, such a good results. So what is going on here? You might ask me. First of all, it very depends on your dataset. There's no guarantees that, like, if you will use the pre-trained equal to true, you will get the same results. It very depends on the dataset which you're going to use. But let me explain you why the results are so good. The thing is that, so in ImageNet, there are 1,000 classes on which this model has been trained on when the pre-train is equal to true. And the thing is that, like, almost all of the monkeys, all of the different monkey species, which we're having in our own 10 monkey species dataset, the same species exist in the ImageNet classes. So basically the ImageNet already has seen a lot of examples of these monkeys, and the neural network just learned how to classify them. And there are millions of images inside the ImageNet, which means that, like, this neural network has been trained on the greater amount of images. Not like, I don't know how many we have, about 1,500 in the dataset which I'm using, which is like almost nothing. So on the ImageNet, it has been trained like on thousands or maybe 10,000s, maybe even 100,000s, but probably not. But like, it has been trained like on a much more images, and this neural network has seen like much more examples. So that's like a bit of cheating, because you're kind of reusing this already trained neural network on the bigger data set, and you're just training the neural network just for your own data set. It's a cheating, but it gives a very good result. So however, it's a good practice to apply the pre-trained equal to true when you're using, for example, ResNet or some other neural networks which have been trained on the ImageNet, because probably it will give you better results, and it will speed up the training process as well. Like, even, for example, I don't know, let's say you're building the neural network which will classify, let's say, 1,000 different cars models, right? So ImageNet, for example, can classify, I don't know, just a car or a van or I don't know, police car, something like that. So it can classify different car models. Like, it can distinguish between BMW 5 and, like, I don't know, Honda Jazz, let's say. But it knows how the car looks like. So if you start with the pre-trained true, it's like the weights inside the pre-trained model, they already know how the car looks like. For example, it has seen a lot of different cars, And if you just will retrain your neural network, which before that has been trained on ImageNet, probably, first of all, it might give you a better score, better accuracy. Secondly, you will need much more less epochs because it will just speed up the process because it already has seen, for example, how the car looks like, and it has seen a lot of different cars. So it will give you an advantage. In this case, yes, it's a cheating, but the results are good. So I have showed you two different options, and you can try both of them, for example, for your own data set and choose the most appropriate one for you. But here, usually the pre-trained is equal to true. It will give you a better results. That's it for this tutorial. Guys, I will see you in the next one. Make sure you subscribe to my channel and share this video with your friends. If you have any questions, guys, please leave them in the comment section and I will try to answer all of them. Good luck and take care, guys. See you in the next video.